All right, welcome back to Cohort 8. So, we are in the first discussion of Chapter 4. Where would anyone like to begin? Could be any section of 4 or any question or where 4 fits in or just anywhere anyone wants to begin first. Yes, Sylvia.
I found this chapter quite heavy in math, and I'm still working through it. I'm just wondering like how much of the math is required to know for like modeling or for being able to go through papers in the field of active inference. I suppose we don't have to like know everything by heart, but like which figures or equations do you think would be very essential to go through to be like the foundation for understanding active inference?
Yeah, what does anyone think on that?
I'm sorry, I was looking through the textbook. Seems like a question for.
I think it's a super interesting question. One piece that comes to mind is like how much math would be required for doing uh neuroimaging like SPM modeling or just any other kind of statistical using a linear regression in Google Sheets or Excel or R or Python or using a some sort of statistics. It's like there's a lot of math that stems from and describes and kind of gives rise to those statistics equations. And same could be said for going into the like, what gives rise to the linear algebra or the probabilistic systems part. So it's like this is a really a critical and kind of that is the question. Like we get to chapter 4 and it's like, okay, this is where the two roads came in from both sides, and now this is where it actually is going to be. All right, this is the key piece, but how much do we need to know in order to do different things? And just how much of this is um perhaps from like just background, even though it's hard to say what's the background and what's the key piece because clearly this chapter was written to try to at least give a uh some balanced but minimum blend of true background topics like fundamental properties of probability distributions, logarithms and derivatives, um, probabilistic models, that have reference with about observations and actions. So we can continue going on, but I think like those kinds of statistical models could be applied and useful with or without understanding or being able to know all of this. Um, however, it's good and kind of needs to be at least understandable how the tools and the implementations relate to what their formal structures are. What does anyone else thinking about it though, because definitely that wave kind of hits hard in chapter 4 with just being kind of half equation-y.
I don't know. My personal feeling is that the equations and the sort of computer modeling seem to be kind of disconnected from each other in practice. I just get that feeling.
Do you feel that way for like using linear regression models? Like just using statistics in papers, the way that p-values are used? I'm just curious. That's kind of just where I calibrate the question to.
No, not in the same way, because all these equations are supposed to like represent things in thermodynamics, and I don't see any thermodynamics in like the computer models.
Yeah, I think this is something that's a an interesting ambiguity or sort of juxtaposition or like a namespace crowding with like energy-based models. So there's like energy as the potential and the kinetic energy of some object in mass, for example. And this sort of sense of using an energy function to fit some statistical model. And then there's like if, whether, how that actually connects to thermodynamics, like candles burning and the energy density and like temperature dynamics. But it's possible to make these energy-based models that but it's not talking about like energy in the gasoline burning. But that's kind of like they are in different domains, right?
Yeah, well, so I understand that the word energy in AI can mean all kinds of things. Even in math, like for example, there's something called the Dirichlet energy, which but my understanding was that this was supposed to tie into thermodynamics, and equations were supposed to be interpretable as thermodynamics.
Yeah, there's a few kind of separable angles on that. So if you follow the Bayesian mechanics, um, it like Dalton, Socrates-Devel, and that line of work, then it's like generalization of thermodynamics, just in the same set as the Newtonian, the thermo-informational, and the quantum mechanics, Bayesian mechanics being like describing those belief distributional updatings and other. So that's one sense, but that doesn't mean that it has to connect to thermo in terms of describing the energetics of systems. It still could just be you could just be talking about some Gaussian distribution doing some rotation. It doesn't have to like tie to the actual survival of some embodied object. But then there's that second angle is like, is this relating to the actual thermodynamics of systems and how they maintain themselves above and beyond what just not dissipating, which is like the kind of autopoiesis. That's just sort of how even qualitatively the biological systems are framed. So just but that's a little bit of a separate um question almost or area of applying it than just trying to generalize the theoretical physics of information systems.
Daniel, if I could jump in real quick, uh,
Yeah,
I,
please.
I really appreciate the way you bring so many disparate fields together. And I also appreciated Sylvia's question. Uh, there's so many levels to talk about this, but I think it's really important always to circle back to the principle because that's different than the math. The, the principle of free energy being a framework. This is where I've come to understanding that it's really important to understand the framework. It is a framework that is applicable in so many different ways. And I had to go back and look up Helmholtzian free energy and the chemical free energy, all in terms of thermodynamics. They can be contextualized under different conditions, but really the principle provides a framework to apply so many different fields, which I think is the brilliance of using this framework. It allows using a structured set of equations that really you could go into with a lot of depth, but you have to understand the language, what the symbols mean. I think this was sort of getting at Sylvia's question. You have to understand what the terms are, how to construct the equations in order to be able to construct particular applications. But there are so many tools to use. In terms of what John was talking about, the computer modeling is more about classification, whereas the mathematical equations are just giving the rigor to the context. I want to hear you talk about this more, Daniel, but bringing in those who want to apply the principle to these different applications, whether it's on the molecular level or the social level, the framework can be used. I really think that's the value of the free energy principle. It's just a common language that can be used in all these different applications. And even if a person doesn't know what the symbols of the math means, they, in consultation with others, they can find that out. But just the understanding that it is a consistent, universally applicable framework of how systems evolve in this free energy principle, no matter how complex it is. I don't know if that's helpful, but this is just my approach to contextualizing all these different layers, these different applications. It's centered around this principle.
So on Helmholtz free energy, so it looks like the sort of Friston free energy is supposed to be the same as, in addition to other things, the Helmholtz free energy because of that energy and entropy term where they talk about it being proportional to energy, the proportionality, of course, being temperature. But so the weird thing is that energy term comes from the Boltzmann distribution. And so I'm wondering if there's a more general form of the equation that can deal with other distributions, and in particular, one thing I worry about is the Boltzmann distribution is 1-to-1, right? But if you have some distribution that's not 1-to-1, say a Gaussian, then it can be, then trying to compute the energy from the probability isn't going to work because you don't have a 1-to-1 function. I'm just questions like that.
Yeah, the lot to say just to these last points. This makes me think of this one paper, which I'll put in there. Like, what makes an equation an energy function? I'm actually just at some, there's probably lots of levels to answer this. What makes something an energy function? What makes it a free energy function? And then like, what are all these different flavors with adjectives or with last names? Like, oh, this is this approximation. How many layers deep into qualifying, like what kind of it is? matters for the FEP, and how many flavors of that matter for applying. Like that does it are there in practice across different settings, or is it gonna get super tied down in the weeds with needing to specify all these really different settings for and like slightly different unjustifiable assumptions will lead to very different approaches with um different like computer approximations, or will like just multiple pretty different approaches give broadly similar results. So for example, in the SPM textbook, there are chapters that have elements with classical parametric statistics, Bayesian statistics, and non-parametric statistics. So like the bootstrap and shuffling and relabeling techniques, like procedural techniques to randomization, and these and the classical and the Bayesian form of statistics, and probably things like conformal or other statistics too. It's like if there really is a warmer room and a cooler room and the thermometer has non-zero information, you pretty much should be able to detect it somehow. So that's the kind of empiricist part. And I think that and this is a perfect chapter for question, because it's like, okay, low road was just about making the computational building and assembling the joint distributions for Bayesian models. High road is more theory and axiom driven. So then it's like, okay, so how general or relevant is this meeting point? Is this like every single model, like even just a linear regression? You can interpret that as doing some process describable like this. Like, does this just redescribe and generalized statistical methods? Or what is really being said or claimed beyond what?
Well, you asked the precise critical question. What are the important constraints in constructing your model, one's model? What are the important variables or factors to consider? Like, is the noise randomly distributed and independent or not? That determines what kind of statistics you're going to use. Is it a constant pressure system for a Gibsonian free energy, or is it a constant temperature system for what is it, Hamiltonian or Helmholtz? It's could you consider the activity of neurons in the brain as a more or less constant energy but redistributed? It really is a creative process in figuring out how to construct the problem. And I think that's why it's helpful to understand, here's the framework, here are the tools to use. Now, how can we rearrange the problem to make the appropriate assumptions, to use the formula in the proper way? And that's going to take a lot of, I think, collaboration or individual brilliance, but collaboration would be more helpful to me.
Yeah, those are great comments, and it reminds me a lot of complexity science and system science. Like, also that is about a framework and approaches about patterns and systems of different scales. And also has long featured agent-based modeling, like using NetLogo, and other agent-based modeling approaches. So that is a big part of it. Is and then where where do the so just beyond that qualitative structural possibility of complexity science, what do we really get with chapter 4? But it helps connect all the way to a statistical, like looking at neuroimaging and SPM. And so thinking about first in pre-FEP working with just this one defined data input type, like fMRI data, or EEG data. And so kind of constraining on what the input data were, and then seeking to make cognitive inferences about perception and action. So that, and then it kind of built many of the empirical precursor threads, like fitting latent space, fitting empirical data, noisy empirical data, finitely. So that's kind of the connection point with the empirical nature of data in like research, um, with projecting onto latent spaces, whether just generalized dynamical systems latent spaces or information spaces like probability distribution spaces, which is a space where there can be more axiomatic constraints on like thingness. Which in many situations can be kind of like just a tautology or an auxiliary point or overkill related to just statistics and practice. But it gives a lot of touch points with some of these statistical information underpinnings, which then tie into, at the very least, like the efficient ways to model and identify systems empirically. And then I think there's like a lot of going further than that to this, like again, to that second angle, kind of like to John's question, isn't this about the thermodynamics? It's like, but isn't this really about information processing? Not just doing Bayes optimal statistical modeling of empirical data. Like Chris Fields' course wasn't about saying, here's how you fit the models that balance the right number of parameters with the right, not overfitting the data. Where like complexity minus accuracy is just a normal measure for not overfitting a statistical model. But that doesn't need high road, or it doesn't need a chapter 4.
Here's a question. How would you determine the actual free energy of, say, I have a cat here. How do you determine the free energy of my cat?
It's like, what's the mean squared error of your cat? It's like a model specific. If you're looking for a number, it's just a feature of it, we can look at equation 2.5, but it's not like it's defined outside of a given distribution as modeled.
Right. Well, so one issue is that the distribution is the Boltzmann distribution, right? Because you can tell that from the energy equation. But the Boltzmann distribution assumes that you have a closed system and that the energy is constant. But a cat is an open system. His energy can change when he runs around or eats. So like I this is a thing my physicist friend brought up to me is how do you determine how do you actually use this on a complex system?
John, real quick, that is exactly the question that I ask so often. How do you set the bounds of the system? Clearly, ultimately, you're talking about the universe. But if you're just talking about the cat, you have to make certain assumptions for the moment, for as an approximation. And I know you like complex systems also, but you can set the bounds of the complex system even as
But
a temporary approximation.
those kinds of approximations will only work if things are of the right scale. So if the energy is changing fast enough, then it's not going to be approximated by a Boltzmann distribution, right?
Yes, and then you have the hierarchical levels. I think this is also brought up, not in this chapter, but uh, you just layer and layer and layer your models.
Exactly. Great point. So there's probably a lot in what you said there, um, John, and like identifying the right scale. So one sort of practical note on this is like it may just be constrained by the data that's being obtained. Like it's just fMRI data. So it's constrained versus the more like open multi-scale inquiry. And then just like Stephen said, like this is where structural modeling and nested systems, but also there's that kind of Bucky Fuller, like starting with universe idea and kind of begin and then discarding irrelevancies and like the subtractive method to identifying systems boundaries. And then just in terms of model identification, that's where you do structural just like you could do with the clinical data. Like they just make nested the model comparison amongst um every single variable, every joint, and then just ask, does this model with more parameters explain more? Does it have more accuracy minus complexity? Given explaining the variance in this data set, given the number of parameters. And then but treating that as a model selection, model inference task, like model selection as inference, and then identifying. So okay, so we have data coming in on a continuous spectra, and then so compare how many different ways to partition that. Should there just be one Gaussian? Should it be a mixture of Gaussians? Should it be a mixture of nested Gaussians? But in a given situation, I might be like over exploring. But some of these are pretty well typed out, at least in theory. So being able to do at least kind of broad sweeping, explore a few structurally different hypotheses pretty fast. And it's a super rich question. There's a lot to explore in theory, but in practice, it might just be easy to identify. But it's pretty fascinating that there's also a lot to explore in that question about like the general systems theory and nested systems in their general interactions, and that may lead to some interesting new possibilities in real world systems. But in terms of like what data is available, be like we have um 10 replicates per person from 3 different conditions. It's like, well, that's the hierarchical level of the statistical model. So that's just more just making statistical models that recapitulate the levels of identifiable structure in the data.
I'd like to point something else out, which is the the the, the combination of, in the framework, the a generative model and uh, uh, picking an appropriate generative model within this framework. And just to point out, in the brain, there are different generative models being used. Like in the visual system, there's this convolutional network, and in the reward system, basal ganglia, cortex, you've got this reinforcement learning generative model. They're different types of deep learning models, but they can still be, but they're still within, if in our world, they're still within this free energy, Bayesian type, most probable selection process.
I guess my question can be phrased as, if my cat, say, wasn't acting to minimize his frisk and free energy, how would we know? Like, what test could we do to find out whether he is or not?
And again, it's not really a question of, in my view, exactly that what is what is happening, but rather how can we formulate it? How can we describe it? And really, all free energy does is provide an upper bound. It's like it's accurate enough for the task. It's complex enough for the task. In terms of how we describe it, we can make predictions about what's happening. We can model this system as, again, using the brain as a reference. There's a system of actors that are reacting to what's happening in the environment. And the way that they're formulated is in response to what's happening in the environment. There are created these priors, and in behavioral interaction with the environment, there are these predictions of what's going to happen. We say predictions, but it's really just the way the system is set up in a developmental response to how it has been interacting with the environment all along. Nothing springs out of nothing. It's a developmental process, and this is how the free energy formulation is a great descriptor of that process. It's a great framework for thinking about how that process occurs.
I get that you make models and then you use the models to make the predictions, but if you want to make a model of my cat vis-a-vis its free energy, you're going to have to try to figure out what his free energy is. And that brings me back to my previous question of, how do you figure out the free energy of a cat?
Well, what's your model of a cat, I think, is the question.
I would like to be able to predict the cat in the future. It's what you said. You have to
predict.
the model
to predict just the body temperature, or blood sugar, or the location, or cognitive.
Let's say location, because that one's complex enough that it brings up the problem. How do I know where he's going to run to?
So
that's probably doable, actually.
Yeah. So you have a location in 2 dimensions in the space. There's some distribution over X and over Y, or there's some probability kernel summing to 1 spread out over the zone that you're going to be modeling this. So then it's like there's some diffusion process or there's some other underlying stochastic process giving rise to samples coming from some true underlying latent distribution. And then it's like if you're using GPS or a video or just spot sighting, you're getting some empirical observations of the location of that cat.
But what if but if you do that, like what if the variance is too high to do anything useful with it?
Yeah, big picture, the whole point of statistics as a framework is so we can differentiate between like where do we have a super tight Gaussian and where do we have one that's so washed out that it's just like a flat line, like it has infinite variance or something like that. So big picture, that's the whole point. Be able to do estimates of variance, like, hey, we haven't sampled enough to reduce our uncertainty. And that doesn't mean that with some other prior or some other framework or framing, there isn't information on data set. It just like those observations hitting that distribution resulted in a washout, which could be a false uncertainty. So it's not that any model is going to be like, et cetera, no free lunch, but that is the doing of statistics, is determining the information content and the relevance of the data on updating your prior and understanding whether you are just getting your prior back, or whether you're actually picking up with variable starting positions in prior families, similar tendencies in data.
But for something like a cat, in order to get a variance that would be low enough to actually do something with, wouldn't you have to like model like the whole brain of the cat? And this would bring in issues of how do you estimate the cat's free energy, right?
No, you might just have a spatial temporal kernel learnable through any number of means, including just all kinds of methods, deep learning, parametric statistics. There might be so many ways to reduce your uncertainty by many bits about where the cat's likely to be. You can make a transition matrix by room, and maybe just there's a circadian cycle. Now, where that exists between providing no information, like its behavior's encrypted, like maximum, or whether it's super recurrent with a high information learnable content, that's just an empirical question.
Well,
But
I think people would.
there's no ability in modeling any given situation or whether there's a given signal for you in any given data set that it's just it doesn't take down statistics as a framework or bypass it. It just means there are situations that are with high identifiability for certain modelers or not.
Well, I think the idea that his behavior is encrypted is sort of accurate because animals are supposed to be unpredictable to other animals. And so for that reason, I think you would have a very high variance and you wouldn't actually be able to model it unless you were able to model all of the sub aspects at the lower scales. And then that sounds really, really hard.
Well, John, it needs to be unpredictable enough. It needs to be also conversely predictable enough. Like there may be vast stretches of time where they really don't want to be predictable, but then there are other local stretches of time where they want to be very predictable, like when the food is going to be there. So they're going to be, again, you don't have to know everything to make the model. There are going to be black boxes.
So in chaos theory, if you want to model something linearly in time, you have to have exponentially more information.
Again, this was Daniel's point. It depends on how how fine grained you need to be.
Yeah.
Let's say I want to know what square foot he's going to be in for the rest of the day.
Yeah. Yeah. Like what performance you get with what input data and what spatial grid and what kind of reliability you need in the statistical model, that those are the exact questions that are important for statistics in practice, like data engineers, behavioral researchers, like doing statistics and determining probably all other kinds of data analysis questions. But this is the meta science of the approach to to have an open-endedness structurally in these settings, and just practically to explain data well, and in practice to use a multitude of statistical and non-statistical methods.
And also sampling methods. Like if you want to know the square foot location of a cat, you're going to have to at least sample, half square foot resolution of the entire space, the closed system.
Well, I think you'd have to sample more than just location. I think you'd have to do all sorts of sampling about the cat's nervous system as well to get the variance anywhere near low enough to use for anything.
So that's again an empirical question. Are you going to have, is your model constrained to just sampled location data in, latent location data inferred, and or are you opening up this structural possibility of, well, what if we do latent state inferences? Like, what if we also have this other side information? Or do we want to include temperature in the room? Or do we want to include the season? Like, what other variables should we include? How should we mix and match and compose and flow these variables? Hitting it with the all by all statistical analysis, which it might be doable in certain settings, but you're right that it scales computationally poorly. Whereas for interpretability and efficient computing, the sort of goal approach is a sparse model where the sparsity corresponds to like the sort of cutting nature at the joints, doing actual relevant identification of ontologically real systems, caveat, what is real, what is useful, but just aiming somewhere in that useful direction, and in a less and less predisposed, more and more structurally flexible way, do multi-scale systems identification, knowing that analytical systems identification a certain way would be implementable just with certain, knowing that there are computational tools to implement the models beyond just sort of, let this variable represent this and let this represent this, and kind of just purely going off into a symbol direction.
I'm just wondering if the free energy principle can be tested on animals, or if it's just not computationally going to be possible to do that.
Like, does applying it to choice behavior counts? Or are you talking about like the what the textbook calls the whole iguana? It's like,
I don't know. I guess I would be happy with seeing something impressive that couldn't be done by another means of analysis.
Well, if I may, it's also applied to social systems. I mean, there are several papers on psychiatric applications, and it seems to be pretty successful. I think, correct me if I'm wrong, Daniel, but I think baked into this approach is the probability of the how important, the probability that unknown variables are important or not. You may not know all the you may not be able to model all the variables, but
Well, that's just sort of the variance, right?
well, yes, but there are different kinds of variances, well, yes, different kinds of variances. You're right. That's what we're talking about. That are being iteratively adjusted. Updating the priors in order to get a more accurate probability spread, complexity, the variational probability.
I just wanted to jump in as a novice here, and you mentioned the priors, and you also mentioned other approaches. I'm wondering if this is, I guess it would be an application of free energy as opposed to another approach if you're doing updates based on uh, new observations that generate prediction errors. But I'm thinking, looking at my cats. How much do you weigh just priors? I mean, if you were to just ask me, hey, as a relatively lay person in this discussion, like, where do you think your cats are going to be in a given time? I say, well, what time of day is it? This is where they are. This is where the sun is, and so like a lot of the variables seem kind of predictable. So then you've got this really strong prior, and your generative model is probably fairly predictive. And then I guess the next thing is, well, then how do you add to the complexity of some of the unknown variables? There's a loud sound outside, things that are unexpected, right?
I'm looking
Yeah,
at
that was a great point, and it's kind of like the figure 4-2, thinking graphically, and what is that Lego toolkit of graphical assembly, diagrammatic assembly of observables and unobservables. So it's like and then which, and that kind of gets into abductive processes, um, model selection, structure modeling, selection amongst statistical models. But especially once you can create unobservables or do latent state inferences, you could do, I mean, arbitrary chains of latent states that can be transformations or interleavings or just different patterns. Like one pattern that people use to model the brain, like there's convolutional like patterns structurally. There are hierarchical predictive processing like functions. This is kind of like Mars level of analysis. Like what are the algorithmic and the cognitive and et cetera layers, or what is happening, and then how is the structural, the real dendrites and glia and everything, how is that structural mechanistic layer for different embodied systems or silicon chip or whatever related to the symbolic diagrammatic relationships of observables and unobservables and different transformations.
John, you brought up a philosophical question, actually. You may think you're wanting to model your cat, but there's no such thing as a cat. There's a population, and a cat is a member of the population, but it doesn't exist independently. I mean, again, I'm talking philosophically here, really. You want to model everything about your cat. But you're absolutely right. To model everything about your cat, you'd have to model the entire universe, or at least the entire world that cat inhabits, every place, including other cats and everything
Yeah,
that it interacts with.
But what I'm worried about is, like, what if he's not lowering, what if he's not acting to lower his free energy right now? How would we know? That's my fundamental question is uh maybe he's acting to lower his free energy and maybe he is not. How do we know?
Well, isn't free energy just an upper bound to uh, the difference between the complexity and the accuracy, or the divergence and the evidence? You know, it's
Well,
not it's
well
not a
maybe
precise number. It's just an upper bound to what the difference between the energy and the entropy is.
Yeah, but that's one great point. Let me give another piece on this. Here's in chapter 6. Complete class theorems state that any statistical decision procedure, so whether it's ruminative, repetitive, maladaptive, just leading to demise, leading to peril, externalities, failure, may be framed as Bayes optimal under the right set of prior beliefs. So, whatever, whether the
okay,
cat
so
is staying in one room or whether it's between two rooms or whether it leads to its demise, that can be tautologically modeled as its own as a distribution. So there's no sort of perceived or projected pathology on like human or a cat system or any behavioral situation you can dream of that couldn't be seen from a modeler's perspective from the outside as a statistical decision procedure.
okay, so are you familiar with David Deutsch's criterion of good explanations?
No.
So a good explanation has to have something called difficulty to vary, which means you can't just change all of the details, which means that if if you had a negative experimental result, you can't just change the details to get another one. Um, like if the idea is you just go through the enormously large space of all statistical models until you find one that says the cat is minimizing its free energy, unless there's some concrete way to actually check whether that statistical distribution applies to the cat in some way, that you're not going to have difficulty to vary with an explanation like that.
Yeah, it's what if you think is it possible to talk about the statistician reducing their mean squared error for their predictive model of the cat? Like, do you extend that sort of belief to all of statistical modeling and just doing behavioral science? Because that's a separate avenue than asking what the cat is really doing and taking this sort of like ontological, like
It, it,
what is
it's
the
just
what is
that
the territory really doing is a little bit of a extension to the systems identification question. And so it's just what they're a little bit different application questions.
it's just that cats are sneaky and they're temperamental, so they may decide that they're not going to lower their free energy because they want to confound us. And so how would we know that they're not?
I
I'm sure
just
there's a ton of ways to think about it, but just like from a complex systems like or system science, general systems perspective, I just think any particular data point you throw, cats are sneaky, or this, I think this will happen, or they're like this, or I saw this, or I don't think that's possible. It's like we're looking for something that includes all of those expressions, but just like, but then this mushroom did this next to this tree, so how could that be doing that? It just those are all inquiry directions, but the whole point is what is the grammar of all of those identifications and assertions that you're just saying in a row. There's
I'm
a
just
bigger, so it's nothing about cats specifically. It's just what is the language that you're looking for a design space within with those kinds of claims you're making about your cat.
Well, it's sort of, where does the probability distribution come from, and what does Bayesian inference add that wasn't there before in trying to figure out the probability distribution?
Yeah, fair enough. I think you're asking really good questions, and you try it and see if it works.
Yeah, that's a great way to put it. And I also think about like, are we talking about modeling a situation relative to just vibing and not modeling the situation? Or or are we talking about the difference between Bayesian statistics and parametric statistics and non-parametric statistics and deep learning? Is it methods comparison within we're already in a probabilistic modeling technical sort of setting? Or is it a philosophical qualitative discussion about the nature of things that isn't really looking to be just deflated or resolved to like, yeah, what is the free energy of marathoners at this mile? It's like, well, are we talking about their temperature? Okay, well, here's the data set. Here's the value.
I,
It was 2,700.
Okay, let me put it this way. So my question can be phrased like this: if I'm trying to model something by introducing some kind of probability distribution and using that to model it, what do I get out of using Bayesian mechanics that makes that better than it would have been without? So, anyone could just start from first principles and try to model things with a probability distribution. How does that modeling process change if you're using the free energy principle?
Yeah, it's a great question. And I look towards more and more really cool, documented, more explainer paths through that. And so beyond just looking at the literature and the citations for what are described in this textbook, um, one, I'll just give two short ways. One way is like as a perspective and a stance, this is like how information is like using this as as part of our toolkit of information theory and understanding statistics. It's like this is just how statistics inference is. If your joint distribution that you're looking at is just it's a lens on what statistics have already occurred. You just look at the statistics in a clinical study or a behavioral study. So in that lens, it's just a way we can think about even those statistical analyses. But then as we start thinking more into Bayesian graphical models, it gives composable probability modeling tools. And then you can do statistics modeling and have these diagrammatic tools. And there's other situations where it's convenient and more than adequate to do like to think more about a data science flow chart. Like here we're just going to push it through a neural network and get the output. So that's thinking like at a systems engineering level and just letting a ton parameters with a ton of models with a ton of parameters just learn relationships in data. Here's an explicit probabilistic distributional approach that has some other features.
And those features are, it plays well with other techniques, other models. It allows interaction, translation between different approaches. You can start with a very coarse-grained approximation and update it to make predictions in a way that can be interactive with other approaches, is my view of this, is the advantage of using this approach. It gives you more tools.
Yeah, I think that compatibility of free energy with other, I guess you could say simpler models is appealing, and also it seems that if you reduced it to its simplest application, it also holds up. So in other words, there isn't something that's too simple to um, to be addressed with active inference.
That's a great point that with simple dynamical systems, we can get into the trivial and the inert, like the function y equals 5. It's like, well, that's overkill to have a function to have just this line going for infinite time at 5 when we could just say the number 5. It's like, yeah, but then it's kind of like it has all these other features. So there are statistical models that would be useless or overkill or underkill. That's the whole model selection question in theory and practice. But in terms of the latent space structuring, it can be um a coin flip world, or it can be all this structured latent spaces and structural models with different state spaces, different time concepts.
Can I suggest that that's actually a criticism of active inference and the free energy principle, that it is so available to interpretive description that it can describe anything depending on how you set up the equations and the models. I mean, its strength can also be a criticism of it in a way, because you really have to trust, I guess, how the models are set up. And again, always the proof is in the pudding, so to speak. That does it work? I have heard people say, well, that it's I don't understand it. It's like you can arrange the components of the equations in a way that it's sort of like having any model with enough parameters can describe anything. But the advantage is it's predictive uh, and flexible enough to bring together different models into one system.
Yeah, this is one funny math like quote to the that point. Um, with 4 parameters, I can fit an elephant, and with 5, I can make him wiggle his trunk. So it's like a, um a, with modeling, well, it's just really what is the role? What is the person's expectation of the role of any of this? Of the low road or the high road? How much work do people expect, or what kind of foundational grounding do people expect in statistics? What do people think is under the hood of a t-test or a p-value, or a Bayes factor? Do people know about the z-score and the p-value, Bayes factor, and they're looking for other criterion for signal processing and empirical systems identification? Or are we pulling back a step? Like, what is the role or the function of any quantitative measure in comparison with just choosing not to do that?
Yeah, so if I have a, a patient in the clinic who can't walk straight, and I build a model that says that there's a part of the brain that predicts uh, what forces are necessary on certain muscles to get to walk straight, and there's another part of the brain that's interpreting the sensory input. that's letting the person know if they're walking straight or not. And I set up a model that would predict there would be an error in one component of this system. There would be a damage to one component of the system. I'm going to now go look in this person and see if there is a part of their brain or nervous system that's not functioning properly, or there's damage to it. And voila, there is damage to this part of the brain. That's a useful use of that predictive modeling.
Yeah, well, a lot of interesting comments and aspects today. So thanks for joining. You could come next week at the same time discussing chapter 9, i.e. on empirical data fitting. So that kind of relates to what we discussed a little bit today. Or see you in 2 weeks. So thank you. Bye.